So thank you very much for giving me the opportunity to be here and talk about our work, in which we try to understand and model the dynamics of wave from the nonlinear to from the linear to nonlinear regime in relativistically magnetized environments, and this in the context of fast radio bursts. So this work was done in collaboration with Amir Levinson, and more recently with two undergrad students that I got for the summer. So the general context of this work is fast radio bursts. So there are millisecond pulses that are linearly polarized, so in the radio bands, and quite bright. We observe, well, they have a rate of about 5,000 events per day in the whole sky. And we know that, so they are extragalactic. We decompose them into repeating and non-repeating. We have way more one-off events. And the general properties that are useful for the talk now are basically that there is some hints that are emitted in highly magnetized environments. This comes from, for instance, for the swing in the linear polarization that we observe in some pulses, and that can at least, for instance, in this case, fits a rotation vector model associated with a dipolar magnetic field. And so we also have strong evidence that they can be emitted by magnetars, because we have joint detection between X-ray and radio emission from galactic magnetars. So albeit in lower energy, in lower energies. So it's not completely clear what are the mechanisms in the extragalactic regime, for which the energy is much larger, with 10 to the 43 erg per second typically. So I will be interested mainly in the regime in the model associated with magnetars. So we typically decompose them into two branches of models. So the faraway models, in which we have an ejecta from the neutron star that escape the magnetosphere, collide with the surrounding environments, form a shock, and the shock emits some radio emission that can propagate to us. And in this presentation, I will be interested in inner magnetospheric emission model. So here I'm just showing one, but basically these models assume that the emission occurs within the magnetosphere. And so this is, for instance, a model that was proposed by Yuri Lubersky and also studied by Jens Mellman, in which you consider a pulse that propagates within the current sheets of the magnetars, compress the current sheets, and enhance the reconnection rate and lead to the emission of radio emission. So I will discuss an alternative model, and there are some evidence that inner magnetospheric model can be interesting, especially in if observationally from scintillation. The first scintillation plane has been associated for some event, has been observed to be mostly within the light cylinder, so well within the magnetosphere. And so I was talking about the change in polarization angle, and we have also some phenometrical fitting that seems to favor emission at about 100 stellar radii in the equatorial plane. So again, well within the magnetosphere. So this talk will be, I will discuss different aspects. I will first discuss the formation and the nonlinear evolution of a fast magnetospheric wave and the evolution into a monster shock without considering any radiation reaction typically, and it's a quite standard setup. I will then discuss, leading from this, I will discuss the dynamics of relativistically magnetized shock wave that we find in this kind of monster shock that I will describe later. And finally, I will include and discuss more the effect of the coupling of the wave that is emitted within the monster shock and the effect of radiation reaction in these highly magnetized environments. So to put some figure and a bit more context and to visualize a bit more the problem, so we consider a dipole magnetic field that is in the force-free regime associated with a magnetar, so a very highly magnetized environments, and we consider perturbation at the surface of the neutron star that can lead to the emission of either fast magnetospheric wave or Alfvén waves. And here I will be interested in the second type of waves which are compressive, and they will propagate mainly along the equatorial plane or within a certain latitude. And so at the emission, this wave will be linear, meaning that the scalar invariance, b square minus e square, is much larger than unity, much larger than 0. And as it progresses within the magnetosphere, it will tend to 0. And this, in the context of a dipole, this can be understood because the electric field, the amplitude of the electric field normalized by the background magnetic field typically scale as r to the 2. And so at some point, you expect that this scalar invariant will tend to 0 at the trough of the wave. And so at this stage, you will have a plasmatic wave that started linear that progressively become strongly nonlinear. And there is also a very interesting work by Dominique Bernardis that studied this in the 2D regime that I invite you to look here, to watch. So, as I was saying, we expect that in a dipole, for a wave, a plasmatic wave that propagates along the equator, we expect that the wave will at some point become nonlinear. And here, nonlinear will mean that the wave will start to steepen. And this is what you see in this movie. This is a particle in cell simulation. On the top panel, you see in black the evolution of the profile of the magnetic field. In blue, the profile of the electric field as it propagates along the gradient of the background magnetic field that is in dashed line. And here you have the phase space distribution of the positrons or the electrons. It's an electron-positron plasma. And as it propagates along the gradient, the wave steepens from this shock wave. And this is what you see at the trough of the wave here. You see that the electric field and the magnetic field become progressively comparable to each other. You have progressive steepening of the wave until it breaks and forms a shock. And so we need to understand the structure of this shock. And if you zoom in on the shock structure, what you see is this. So this is again, the magnetic field in black, the electric field in red. And you see and if you look in phase space, you see this peak that correspond to actually solitons. We call that fast magnetosonic solitons. And if you look in phase space, you will see that these solitons correspond to kind of ring distribution that are unstable and lead to the emission of a precursor wave, extraordinary modes. And this is what you see here. You see the evolution of the shock, and you see the emission that propagates upstream of the shock wave. So these shocks have been studied using numerical simulation quite extensively in the context of planar shock waves. And if you look at the spectrum of this shock, what you see is that there is the typical feature that you observe is that you have a cutoff in the spectrum. This is the Fourier transform, the spectrum of the magnetic field. And you have a cutoff at low frequency, which corresponds to the group velocity of this extraordinary mode. So the extraordinary mode are emitted by the solitons, so they need to propagate faster than the soliton, faster than the shock to overcome it and propagate in the upstream. And so this is just a cutoff imposed by the group velocity of the wave. And you have some peak emission, some harmonic emission. So this is not completely clear, but it seems that the peak frequency scale typically as the square root of the magnetization and seems to be associated with the size of the cavity that you observed here. So there is this kind of cavity here that is of the order of the plasma skin depth, in this case, in the soliton frame, and it seems to shape the emission. And upstream, so in front of the shock. And so if you look at something that we need to parameterize the dissipation rate and the energy that you tap into this extraordinary mode is actually the dissipated energy that is tapped into the extraordinary mode from the wave. And what you see is that typically you convert about 0.1% of the energy of the wave into this extraordinary mode. So now you can use these parameters to kind of constrain what you expect to see and what is the typical frequency that you expect to have in the context of a magnetar. So just to recall, you have this magnetosphere in which you perturb at the foot point of the magnetic field and you generate some fast magnetic wave that steepen, form a shock, and this shock emits some extraordinary modes. And if you use the typical parameter that you expect for a magnetar, And for a wave power of the order of 10 to the 43 erg per second, you can get that typically the wave will steepen of about 200 stellar radii and will be in the gigahertz bands with a strong unknown, which is actually the multiplicity. And the multiplicity is so the number of pairs normalized by the Goldray-Julian density is here extracted from what we have for pulsars, but for magnetars it's highly unknown. So then there are a series of so what we have is that we can generate gigahertz band emission in this context, and there is a series of unknowns that we need to discuss first. I will not discuss it here, but it's a very important point, is actually, can this wave escape the magnetosphere? The dynamics of this wave in this highly magnetized environment is actually not very well understood at this stage, and there are a lot of people working on this and try to better understand this aspect. But something that I will discuss here are actually to model the shock dynamics for this relativistically magnetized system, the typical emission process, and finally, the impact of radiation reaction on the structure of the shock. So if you look at the structure that you obtain from the particle in cell simulation, especially in the early times, what you see is that you have this structure of periodic solitons that are formed. And you can actually build quite simply a single fluid description for these solitons, and for that reduced to this kind of simple system for the longitudinal momentum, the transverse momentum of the fluid, and the magnetic field amplitude, normalized here by the Alfvénic Mach number and the shock velocity. And so you can solve the set of the profile that you expect for this kind of solitons, and you can compute also. So this is the profile of the soliton for a shock velocity or a soliton velocity of or Lorentz factor of 100, and Mach number ranging between 1 and about 200. And so you can actually compute analytically that the typical periodicity of this solitonic structure is of the order of the plasma skin depth in the frame of the soliton. And this tells you that in the frame of the downstream, in which we measure the spectrum of the emitted extraordinary modes, we observe that the typical frequencies of the order of scale as the square root of the magnetization. So indeed, we have that the typical scale of emission is set by the distance between solitons, and we understand the typical scaling. We can also use this kind of set to actually study the emission, the process of emission associated with a single soliton, but I will not discuss here. So, but we can, an interesting point to understand the formation of the shock is actually to model and constrain the way the energy dissipated as it crosses the shock. And you have two ways. Either you generate some plasma instabilities, or you have the onset of chaos. You can get rid of plasma instabilities if you impose that the system is stationary. And this is what we have done here at first when we compute the profile of the soliton. And so as a first step, what you can do is propagate some test particle in this structure to see if the orbits of the particle is stable. And actually, it is not, and you can compute that analytically, but here I'm just showing the phase space diagram of orbits of a single particle across this periodic system of soliton, and you see that they quickly diverge, and so this means that basically the solitons should be unstable at some point. And you can actually solve the system more self-consistently by going to a multi-fluid model. So this is kind of approach that was proposed in the 60s by Dawson in a different context, in which you decompose your fluids in a set of cold, you decompose your plasma in a set of cold fluids. And so instead of having one single fluid, here you have a large number of fluids that are coupled through the current. And you assume that everything is stationary again. And so what you end up with is a dynamical system, and so you can study the chaotic nature of this dynamical system. And you can solve, for instance, with a small thermal spread at the origin, you can solve for the profile that you expect, and you indeed see that, so this is the longitudinal velocity, the transverse velocity of the different fluid, and the profile of the magnetic field. And so what you see is that the different fluids quickly diverge, and leading to a compression of the magnetic field, and you recover the jump condition that you expect from fluid. So we have a way to actually model and understand the shock structure, at least to leading order, and you can study in terms of the initial perturbation, what is the typical profile that you expect. And you see, so if you start very cold, you will end up with a lot of solitons and a quasi-periodic structure. And if you start hot, here typically with a temperature that is about 10% of the rest mass energy of the electrons, you completely kill the solitonic structure. And so if you kill the solitonic structure, the soliton structure, this means that you also kill the emission that is associated with it. So this means that you should have some interplay between the emission that is produced by the soliton and the shock structure itself, because the emission that propagates in the upstream will heat the plasma and change the upstream temperature that will change the structure of the soliton. And so you should converge to some stationary state. And actually, what we observe is that what you obtain from the theory look very close to what we obtain from kinetic simulation. And an important aspect in this, when we want to understand the fate of the particle in the downstream, is to characterize the thermalization scale, or the thermalization in the nature of this thermalization. And so you can see here the progressive evolution of the spectrum of the particle, the fluids, at different stages within the shock transition. So this is the magnetic field profile. This is the spectrum that you obtain at these different points. And you see here the evolution in phase space of these different fluids. And indeed, what you see is actually just standard phase mixing between the different fluids, showing that actually, and that phase mixing is actually sufficient to actually converge to a thermal distribution. So you fully thermalize your system in the end. And we have actually a very good agreement between kinetic simulation and this simple theoretical description that we have here. So I said before that we have a dynamical system. So this means that we can also characterize the divergence rate from the Lyapunov exponents, so the spectrum of Lyapunov exponents, which tells you how quickly the different trajectory will diverge. And so what you see here is the spectrum of Lyapunov exponent on this axis in terms of the Alfvénic Mach number of the shock. And so what you see is that in this region, you completely thermalize, generate entropy and the jump condition and recover the jump condition from the onset of chaos within the soliton structure. But you have a range of values between 1 and 2 in which the solitons are fully stable, meaning that chaos is inefficient and you are in the subcritical regime in which you don't expect any dissipation through this process. And you can run a simulation in this regime to see what this type of shock wave look like, and this is what you see. So this is the profile of the magnetic field. This is the spectrogram of the magnetic field that I show here. And this is just a zoom in on the shock transition. This is the electric field, the density of the shock. And indeed, the solitons are stable, and what you end up is a forest of hundreds of solitons that are fully stable and that radiates. So this is in the regime of low Alfvénic Mach number, so it's not clear that if it has any interest at this stage for astrophysical system, but for plasma enthusiasts, it may be interesting. So, some interesting aspects are also the interaction between the different solitons at the interface between the upstream and the downstream. You see some interplay between solitons that start to couple, and you cannot really see here, but you have some emission within this region. So, I didn't mention that, but in the downstream you see highly harmonic emission that is generated from this very structured shock transition, together with this more standard synchrotron maser emission. So this was done. This is in the regime of low Mach number also, but we also neglect completely the effect of radiation reaction. And so we need, if we are interested in this monster shock, in which the magnetization is very high, we need to include that aspect too. So the radiation reaction can be included quite simply in this multi-fluid model by just adding the standard reduced Landau-Lifshitz radiation reaction. And it has been pointed out that this radiation reaction effects are important for monster shock. And they have also been studied in this paper for a set of reduced cases. So, but we need to have a better understanding of the scaling of the shock transition profile in terms of the cooling rates. So actually you can demonstrate analytically that the shock profile typically scale with this constant tau, which depends on the shock velocity and the Alfvénic Mach number squared that you obtain actually in some regime from the leading order conservation equation that tells you that basically you can rescale two more realistic parameters associated with FRBs from more simple parameters that we can actually integrate in a particle initial simulation. And so more physically what you observe is actually that in phase space you have as your particle crosses the shock, you shrink this the onset of, you kill the onset of chaos because your your distribution basically forms a ring distribution that progressively shrinks as it emits synchrotron emission. So we can now start to see what happens in what are the parameters that are associated with monster shocks. What we expect from actually extragalactic magnetars is that typically the shock velocity for the set of parameters that we have would be order of 10 to the 6 and Alfvénic Mach number 10 to the 5. And from these parameters, what you obtain is that the value of this cooling constant is much larger than 1. And so we expect that it will strongly affect the shock transition. And if you consider galactic class radio bursts, for which the luminosity is much smaller, then the cooling rates the cooling constant is much smaller, and for these cases, we should be fine without any cooling, at least for the dynamics of the shock, because the dynamics of the wave may be different. And so what we look at here is some particle initial simulation in which so it's similar to what we have seen before. We run this fast monoclinic wave along a gradient that progressively steepens and form a shock, but this time with different values of this cooling constant tau. And you see that what you have here is that you have for tau 10 to the minus 3, which is more or less what we would expect for these galactic magnetars, you still have strong emission within the shock transition. Here you have this emission of this extraordinary mode that propagates upstream. And as you increase the value of tau, you progressively shrink this emission up to completely killing the emission for tau much larger than 1. So this is just a zoom in. So this is what you see for the magnetic field profile and the electric field profile in red. And an interesting thing that you actually observe is the coupling between the wave and the background plasma. And this is similar to what we, for instance, expect for cosmic ray modified shock, where you have some cosmic rays that propagate in the upstream of the shock. They exert an effective pressure on the plasma because you have some coupling between the two, and so you slow down the upstream. You form a subshock in the upstream. And so here there is some coupling between the radiation emitted from the shock transition, so from this extraordinary mode and the background plasma, leading to a modified shock transition. And in the case where you don't have any emission at the shock transition, you recover the solution that you actually expect if you just compute the MHD, the typical MHD profile from the system. So I guess I have, how much time do I have? Because I'm done. Oh, wow, okay. Well, I'm at the conclusion, so. So what we have seen is that we have studied monster shock first by using MHD and demonstrating their steepening in the emission associated in the kinetic regime as this scalar invariance, B square minus square tends to 0. We have studied the shock formation, the onset of chaos, and we have seen that in a large range of value, this onset of chaos is sufficient to actually explain the transition, the profile of the shock transition and the thermalization of the plasma across the shock. This model actually gives us some good hints that there is strong coupling between the upstream emission and the shock, the profile of the shock transition as the temperature in the upstream is set by the coupling between the wave and the background plasma, and the temperature sets the shock structure. The temperature of the upstream sets the shock structure itself. Then we have seen that in the regime where the Alvin-Mach number is between 1 and 2, we recover some subcritical shock wave so in which the shock transition size is much larger than the plasma skin depth, and even much more larger than the Larmor radius of the particle. And we see that in this very exotic shock wave, the emission can be highly harmonic, and the structure is, it's very interesting to study the emission process associated with this kind of system. And finally, we have seen that for the radiation reaction in monster shock can quench quite efficiently the emission in the context of extragalactic magnetars or extragalactic FRBs, and that the coupling between the X modes and the upstream plasma can modify the shock structure itself. So there is a lot of things that are very interesting to study in this context. So here I was only studying waves propagating along the equator, but a finite obliquity. I mean, we still expect that has been demonstrated by Andrei. We still expect to have a steepening at larger obliquities, and so it's interesting to study what are the dynamics of these shock waves for a different obliquity of the magnetic field. Finally, I was only showing a monochromatic wave progressively steepening, but what we would expect from perturbation at the surface is actually a spectrum of waves, so it's not clear what it would look like in this regime. We need, for any of this to be interesting for the FRBs, we need to assess if actually this wave can escape the magnetosphere. And finally, something that is more, I think, fundamental for the plasma physics and could be also interesting even for experiments, is actually to better understand the soliton emission processes. At the moment, it's not completely clear. We assume that it's synchrotron maser, but actually we call it synchrotron maser, but we don't fundamentally understand what is the process of emission in this highly nonlinear structure. And finally, there is a very interesting aspect that is the soliton interaction that modifies the spectrum of the emission and the coupling between the soliton and the waves that is emitted by other solitons. So, thank you.
I see Maxime first.
I'm not sure that in application to fast radio bursts, the one-dimensional approximation catches the main energy budget, in the sense that if you have dipolar magnetosphere and if you dump energy into dipolar magnetosphere, most of that energy will be used to open the magnetosphere up. And by Ali's theorem that new magnetosphere will have larger energy, and dumping more energy won't help because you will just open it up earlier. And you need at least, so this is an example that in 2D, opening will require 2D. So
but why do you need to open the magnetosphere here?
It will be open. That's how, if you dump a lot of electromagnetic energy into the dipolar magnetosphere, that energy will be spent on opening it up, and that energy will be stored in the newly open, distorted magnetosphere.
I mean, I can agree that like this one-dimensional is highly reduced, and there is a lot of effect that you neglect. So we would expect that we would have also some pair creation that is maybe important and affect the dynamics of the system. So here, I'm not claiming that you are resolving the overall dynamics of the magnetosphere. It just tries to understand the dynamics of the wave itself as a first step, which is, I think, already quite important. But I agree that there is like a global aspect that cannot be neglected. But yeah.
So I was wondering about the escape case. So So because it's interesting the fact that if you let this wave escape, so what do you think would be the effects on the current results that you're getting? Like how things will change if you allow escape?
If you allow escape?
Yeah.
I mean, if they escape, what?
Like for example, like in terms of like if you have like for example if you have like test particles and you have your chaos, so now like for example the Lyapunov exponents are going to start to look different because you're allowing this energy to escape, so the spectrum is going to look different.
So when I'm talking about escape here, I'm mostly talking about the escape of the precursor wave. So it's assuming that basically you let the wave, the fast Mann-Sonic wave dissipate, you form these extraordinary modes that are somewhere trapped maybe between two pulses, and we are just looking at, we are just interested if those waves, can they actually escape the whole system, the magnetosphere? The shock is already gone at this stage.
So it's perturbed by this.
I mean, it's just, we are just looking at the escape of the wave, not the interaction with any
no,
shock
with the
here.
particles and stuff, yeah. Thank you.
Very interesting. Thank you, Arno. I have a question on the radiative part. I was wondering whether you can comment on whether the solutions are steady state at this point. You mentioned this effect, like cosmic ray-like precursor effect, which is slowing down the flow, probably causing less efficient precursor wave. So is this like a repeated cycles, or this is a steady state already?
I don't know. So it's not steady state still. It will still evolve, and as you load more wave. So I'm not completely sure. I think it would be what I want to do now is to actually look at. You look in space how the spectrum evolves, because I would expect that the spectrum will highly depend on space. So in the same manner that you would expect that cosmic ray modified shock the spectrum will soon evolve at different distances. So yeah, it's not stationary. No.
Did you try to study these monster shocks in 2D and 3D? Because usually, so in 1D, the pictures appear way more coherent than when you go to multi-D. If you add like a degree or degrees of freedom to your system, usually the range of those stable soliton-like solutions are drastically diminished. So could you comment on this, or just maybe like, so just, and another one, did I get it right, so that the solitons exist if the Mach number is between 1 and 2? That the solitons exist if the Mach number of the shock is between 1 and 2?
The solitary structures are stable between 1 and 2, but they still exist above.
But I mean, so but they get dissipated.
Yes.
Okay. So, but if you go to 2 and 3D, what do you think? So, just are you going to get the same stable solution?
So, if you consider a planar shock, you should get the same solution. It's and this is actually related to the work that Dominique did. And he has a poster here, and he did simulation in 2D, and I mean, there is differences in the. I don't think there is strong differences in the shock structure itself, but the global structure of the shock in this oblique in this magnetosphere is quite different. So, I mean, yes, but the problem with this kind of 2D or 3D is that it's very expensive to do. This is much simpler to do because you can just follow a small part.
Is it a matter of ratio of that effective Larmor radius to the size of your magnetosphere? I mean, that separation between your soliton and the Larmor radius.
I mean, you need a large separation of scale between the Larmor radius, the plasma skin depth, and the plasma skin depth and the radius.
That probably says that planar is not a bad approximation.
Yeah, beautiful work.
Thank you.
My question is, there's some works by Forslund and Friedberg and Langdon, Ahrens and Max, where they looked at when are these train of solitons dissipated as a function of the particles that are trapped in the field. I mean,
that was in the relativistic regime.
Pardon?
In the relativistic regime.
Yeah. Well, Langdon. Ahrens and Max, this paper is on relativistic magnetosonic shocks. My question is, I mean, what is the fraction of particles that you need to load on the wake, on the soliton structure to get actually the suppression of the train of solitons? or what is the Mach number at which you see this very clear transition?
I mean, as soon as you start to dissipate and the trajectory becomes unstable, I mean, it's basically, I think that in a way that answers the question, is that it's mainly dependent on the temperature of this electron-positron plasma.
Okay.
Is that if your temperature is sufficiently large, it will basically scatter after one crossing. Okay. And so you just have one soliton. That is formed. And then the next one, you just have basically a compression of the magnetic field.
Yeah, well, they have some predictions on this transition. Well, Forslund and Friedberg, they call it laminar shocks to turbulent shocks. So there is, I think this should be kind of a good check.
I think I missed that paper because I didn't read it.
Yeah.
I will, thank you.
Thanks. Can I have Alex and then Chris? Yeah.
Well, thanks, Arno. So, what do you think is, what do you think we should do next to make this comparable, to make us allow us to compare this to our FRB observations, for example? Like, what kind of simulations or calculations we need to let us compare this to, for example, observational spectra or something like that?
I mean, from my point of view, but there is a lot to do already to model the spectrum that we expect from this shock wave. I'm not sure that actually the understanding that we have on the spectrum of just the relativistic shock is very well informed. I think most of the studies have been done in quite low sigma and I mean in a narrow range of Mach number and shock velocity. So I think there is still something to explore in that aspect. But then, like, the first thing to understand is also the effect of propagation of this wave in this magnetized environment. So things that, for instance, Andrei and others are doing. So I think this, and then for the phenomenological part where you can start to fit, I guess you can be quite agnostic about the spectrum that you expect. I think this is what, for instance, Guillaume Voisin did, where he assumed he's agnostic about the emission process, but he just propagates some signal within a dipole and assumed different type of geometry for the magnetospheres. And he seems to show that actually he expects some kind of twisted magnetospheres with strong, larger magnetization within the equator. So from the simulation, I think, what we need to understand is the dissipation from peak simulation or whatever other method, the dissipation, the evolution of the wave in a better way. I think that for me is more interesting.
Just to try and, I guess, sharpen the question that was asked perhaps previously by Lorenzo. High A naught precursor, one can ask, well, if you let it propagate a long distance, is there any trend of weakening of the coherence of the gyrations at the shock?
I didn't check the A naught, but I think it is kind of what we see here, right? Is that you couple this is the Lorentz factor basically, or the velocity, the Fourier velocity, and in the case where you have strong emission, you start to couple the plasma with the wave. So there is some heating and deceleration. So the wave is dissipating as it crosses the plasma.
But I guess the question is, you know, if you have to keep the upstream pairs trans or subrelativistic to keep the maser going, and you let a very, very high A naught wave propagate them through a long distance, you know, even though there are constraints on how long you can run the simulation, can one look for trends?
So your question is over a longer time scale, if you would kind of kill the emission or cycle or just damp. I mean, that's what I would expect, that you reach some kind of stationary states.
But in the galactic magnetized emission, you know, A naught was quite large, that's why I asked.
Okay, Andre.
on the comment. The wave moves the particle in a regular way. So this precursor wave, this electromagnetic wave, and the particle is oscillating with it according to its electric field or potential. And I think it's going to stay regular. It will just follow, it's going to stay coherent, even if you let it propagate for a long time. It's not really heating. Yeah. Even, so the wave will enforce coherent motion. It's like a cold stream effectively flowing. So it's not real heating. It's really the particle follows the vector potential.
Well, if it was just regular motion, you wouldn't observe deceleration.
In the end, of course, when it comes to the shock, yes. But I think Chris is asking, if you let the precursor go very far into the upstream, would it effectively heat up the plasma and then sort of quench the shock emission, right? Yeah. Okay. And I don't think it will do that. I think it will stay coherent until it comes to the shock. And then, but if you run for long enough, maybe, maybe that can be, checked. I don't know how long it should run, but I feel it has to be regular, even if you let it go far.
Could I ask a philosophical question? So if you show that orbit where you thermalize to a Maxwellian, you have regular orbits which break out sort of into chaos and become a Maxwellian. So first of all, it's amazing that this thing with a hole in the middle still looks like a Maxwellian. But second of all, if it is a Maxwellian, is this some kind of fundamental statistical mechanics statement here? That chaos leads to something that looks like a Maxwellian?
I contacted mathematicians in Paris to discuss that.
Oh, then it's
I'm
settled.
still waiting for answers.
I think it's a good question to discuss over a coffee break.
But yes, it's not clear when you have this kind of dynamical system, and the thermalization of this system in this quasi-integrable system is not trivial at all.
But in other situations, is it always a Maxwellian?
For this case, for our system, it seems to be always Maxwellian.
It's amazing. All right, thank you. Thank you, Arno, and thank you, everyone. So, yeah, we now have a coffee break, and we'll see each other at 4.